In order to understand convergence sequence, now we will look at divergent sequence. That is, what happens when a sequence diverges. So, first we will take a divergent sequence because divergence is exactly opposite of convergence. What it means? If a sequence is not convergent, then it is divergent, and vice versa. That is, if a sequence is not divergent, it means it is convergent. So, in order to understand convergence sequence, it is good idea to look at what happens when a sequence diverges. So first we will write the condition of convergence. So what happens when a sequence converges? For all epsilon greater than 0, there exists a natural number such that for all n greater than n, xn minus l less than epsilon. I have written the mathematical statement of convergence in the way statements are written in logic, and what this set tells, these are domain of quantification. These are quantifiers for all and there exist. Mathematics has two extreme quantifiers. One is called for all and other is called there exist. So here we have for all epsilon. This tells from where epsilon come from. This statement tells from where this capital N come from and where this small n come from. Basically, they determine the domain of the variables used, that is epsilon, capital N and small n. So these are not going to change when we negate a statement. This basically determines the domain of these variables. What changes? This type of quantifiers. From where here we have for all, here we have there exist, and here we again get for all. So when we negate this statement, for all become there exist epsilon greater than 0. This there exist will become for all n belongs to n, and again this for all become there exist n greater than n. So domain should not change. If epsilon is greater than 0 here, it should be also greater than 0 here. It does not mean that epsilon should change its domain, that is less than equal to 0. It is quite tempting, but this is not the case. Domain should not change. So what changes? Basically type of quantifier reverses. Okay, for all become there exist and there exist become for all. Now this final statement actually will get negative. So we know that if A is less than B, its negative will be, its opposite will be A greater than equal to B. So negative of this will be this, and what it makes here, that xn minus L greater than equal to epsilon. So we get the criteria of actually divergence here. This is the criteria of divergence, or you can take it as a definition of divergent sequence here. Let's try to understand this complicated statement, what it says. And it says that there exists epsilon greater than 0. It means that you have to find some epsilon such that for all n belongs to n, no matter what natural number you take, you will always find a term xn, a natural number small n, such that the distance of xn to L, xn minus L, will be greater than epsilon. Suppose we have many terms of sequence and this is our L. So you have to find an epsilon, okay, epsilon small enough such that no matter what natural number you pick, you will always find a natural number n such that the term after this somewhere here or here, but outside this ball. And actually it has very interesting phenomena that if one term comes out to be, this statement guarantees about only one term, okay, you will get. But due to this structure of n, you will get infinitely many terms outside this epsilon radius. You say how? Then try to understand this. Suppose you fix an n, okay? Then you will get a natural number such that will satisfy this condition xn minus l greater than epsilon. Now it means that you get a term, call it small xn, which is outside this epsilon ball. Okay. Now take this n to be n2. n2 equals, call it n1, small n1. Then you will again get another term which is greater than this, call it n2, which is outside this red circle. So suppose you get x n2 here. Now you fix n3 to be n2. Now you will again get a natural number, there exists a natural number which is outside this ball. So you will get xn3. So in this way you can get infinitely many terms which are outside this radius. So a divergent sequence, a sequence diverges from some L if you find an epsilon. You have to find this epsilon such that there are infinitely many terms which are outside this ball. Okay, there are infinitely many. This is what it means a sequence to be divergent. Now let's try to understand the divergence in our other representation, in which in one axis we assume the terms, that is natural numbers, and on the other axis we have plotted the sequence xn. Okay, so in this way you have to find an epsilon such that this is L minus epsilon, and this is L plus epsilon, that infinitely many terms will be outside this. Because if you take first n1, then this will be our n1, and after that this will serve as a small n. Okay, small n. And if you choose this n2, then this will serve as again a small n, which is outside this region. We want everything to be inside this region, but we got an epsilon unfortunately, so that no matter what natural number you take, you will always find a term which is outside this region. Okay, if you take this, you will get this. If you take consider this capital N here, then you will again get. And if you take again this term to be capital N, then again you will get a smaller n which is outside this region. So this will go on and on forever. So you will get infinitely many points which is outside this interval L minus epsilon and L plus epsilon. And this is what divergence mean, that you will get infinitely many points sufficiently away from this L. And in such case, the sequence are called divergent. Now we will see an example of divergent sequence, and I choose a very simple divergent sequence that oscillates between -1 and 1, and this is simply written as -1 to the power n. So let's see what happens when a sequence diverges. Consider this is the line, and suppose this is our 0, this is 1, and this is -1. So the first term will be here, I will say x1. The second term will be here, call it x2. Similarly, first, third term, fourth term, fifth term, sixth term, and dot dot dot. All odd term are here and all even term are here. If you take epsilon, which is sufficiently small, then you can see that there are infinitely many terms which are even terms which is outside this radius. We know that if we can find an epsilon such that around a point, if infinitely many terms are outside that circle, then the sequence diverges. Here we can find such epsilon. So we can say that this sequence does not converge to -1. In similar way, we can say that we can find an epsilon so that the sequence does not converge on 1, and actually we can find an epsilon around any point. There are infinitely many terms which are outside these balls, so this sequence diverges. We can understand these things in our function model as well. Here you have -1, here you have +1, and this sequence oscillate between -1, +1, -1, +1, -1, +1, and so on. And if you take an epsilon sufficiently small, suppose you want to claim that the limit is -1, so you can take it is sufficiently small, -1 minus epsilon -1 plus epsilon, and you can see that there are infinitely many points, this will go on forever, which are outside this region between -1 minus epsilon and between -1 plus epsilon. So there are infinitely many points which are outside this region, so we can say that the sequence does not converge on -1, and a similar analysis will work for any number. Suppose you want to say that limit exists on +1, then you can also form a area like this around +1, and you can actually make such area in around any point like this around 0 sufficiently enough that no term will actually lies inside this area, so this sequence diverges.